Hey guys, we're going to be looking at simplifying rattles, radicals on 7.1. I want to try doing a little different. Not going to be like focusing so much on the screen per se on this one because I've actually worked out step by step on every example, and I'm going to keep kind of going back and forth. That way you guys can kind of see. One just touch base when we're talking about some of perfect squares, radicals, and things I want you to kind of familiarize yourself with is we're going to talk about radical roots, which you guys know. If we have the square root of, like, let's just say 16, it's going to be what? 4. But I want to point out something right here if I could. If you guys will look where it's 3 to the 27th. What that is saying is, what number do you multiply 3 times? So that's going to be radical root to give you 27. So that means you go 3 times 3 times 3 gives you 27. So that's kind of what I want to focus on. Same thing right here. What number do you multiply 4 times that gives you 81? Well, 3 times 3 is 9. Times 3 is 9. Is going to be, sorry, 9, 9, 9, and 9 is 81. So I like to think of it as 4 threes, if you will. So 9 and 9 and 9 and 9. And if you did, let's see, 5 right here. So what you're looking at is you have 5. What number are you multiplying 5 times that will give you 243? And they're using 3 just because it's an easy example. So that's going to be, 3 times 3 times 3 times 3 is going to give you 43. 243 when you take the square root. Well, in this case, it's going to be the radical root, if you will. And what they call this number right here, where the 5 is, where the 4 is, that number is called your index number, okay? So let's just talk about the places. This is your radicand, where the 81 is. Where the 4 is going to be your index, all right? And then whatever number you find up here is going to be like your radical. And watch for signs too, whether they be positive or negative. So let's go ahead and swing on over, if we could, to 289. Like I said, this is going to be just a little bit different here because I want you guys to kind of get a little look step by step. So I thought the best way I could do it is actually work it out on paper and let you guys see exactly what's up. All right. Our first one says that we're going to have the radical of, if you guys can see, sorry, negative 125. All right. So let's talk about 2 things here. Our index is what number? 3. And our radicand is what? Negative 125. All right, so what we're going to look at, I'm going to go to my paper right here. I've worked it out where you guys could kind of see. You have index, radicand, it's the cubed root. So that's saying negative 5 times negative 5 times negative 5 gives us 125. So what's the square root of? That's going to be negative 5. All right, so again, 5 times 5 times 5 is 125, but it was negative, so it's going to be negative here, and it's going to be negative also right there. All right, B says that we got our index is 4, our radicand is negative 16. Now, do not think that is saying 4 times 4 gives you 16, all right? That is not what that is saying at all. That is saying, is there 4 numbers that you can multiply if you went 2 times 2 times 2 times 2? Would that give you, or 3 times 3 times 3? No. So there is no real roots or radicals for this number here that will give you a negative 16 evenly, all right? Same thing for, let's look at C. Now, C has 0.16. We do know, just because it's a decimal, you can still have a perfect square. So we know 4 times 4 is 16, so there's a good chance that 0.4 is going to be what? Yes, it's going to be the square of this. So it's going to just be 0.4. That's all you have to do. D is going to be looking just a little bit different. Here you have 3, and in radicand, 27 over 8. So you're looking for your index, which is what number? 3. And it's going with a 27, and it's going right here with 8. So I went over here, if you can kind of see mine, I pulled both numbers out by themselves. All right. So for 27, I figured out that 3 times 3 times 3 will be the cube root of 27. Okay. For 8, I found that 2 times 2 times 2 is going to be the cube root. So that's telling me that right here, my index has a cube root and a cube root. So here, it's going to be what? It's going to be 3 to the third. Here it's going to be 2 to the third. So if you bring that out, what's it going to be? It's just going to be 3 halves because you're bringing out your cube roots. So again, we found 3 to the third power here and 2 to the third power, which gave us 27 and gave us 8. One over here. You still think of it kind of like squaring it to bring it outside of the radical, so that gives you 3 halves. All right. E, here we have 100 million. When you square that, if you just put in your calculator, it does give you 10,000. One thing I do want you guys to kind of look at right here. If you have 10 to the fourth you're bringing out your perfect square, if you will. So realistically, what you're wanting to look at is when you multiply these back together, which gives you 10 to the 8th power, that should give you 100 million. You can always check by counting your zeros, make sure there's 8. And that'll take care of example 1. And I'll post all these online too, these papers, that way you guys can see them, where I've worked them out. Alright, so let's go ahead and look at example 2. Example 2, some of the same similarities apply. We're still bringing out index numbers, radicands, and then we focus in here. Alright, so here we're told that we need to simplify. Alright, so I already see some things I'm familiar with. My index, my radicand. So this means it's to the cube root. So just like we did a second ago, didn't we have something for 8? Wasn't it 2 times to the third power? Well, guess what? It is right here also, because let's go over here and kind of look at my workout sheet, if you will. Alright. So you guys can see right here that I broke down the cube roots. I took my 8, and it's 2 times 2 times 2. And so x can stay, because there's nothing you're breaking it down to for the moment. So next we want to be looking up, breaking down y, because we want to rewrite these in a way that we can bring out. And when I say bring out, what I mean is, since if it doesn't have something, for instance, like this one does, we're looking for familiarity. So we have 3 right here. This was 3. 2 to the third. This is not 3. But how can we make it 3? Well, we can break it down here. Y to the fourth, 3. Alright? Whatever number is right here, you want that on the outside of the parentheses in order to get rid of it at the end. Okay? Because when you rewrite it, you want to be able to break it down. So when I go to rewrite it, I can bring everything out, and that leaves me with 2x, because I brought my 2, because it was 3, brought it out, y to the fourth, because this is now gone, right? Let me bring that out just a little bit so you can see. Okay, let's go ahead and take a look at B also. Same concept, we're looking for something. Oh, I just dropped something. So here on B, we have index 4. In our radicand, we got 81. So that means we're looking for something that we can multiply to itself like 4 times. So that means if it go 1 times 1 times 1, would that give you 81? No. 2 times 2 times 2 times 2, would that give you 81? No. But 3 times 3 times 3 does give you 81. So that's a good place to start. So everything we're trying to break up is we're trying to make sure that our exponents give us a 4, perhaps outside the parentheses. And what I'm saying is, so we're starting right here. 3 to the 4th power gives us 81. Now here we had a to the 16. Alright, I need something that can break this down to give me 4 on the outside. So 4 times 4 gives me 16, so I still got a to the 4th to the 4th. Alright, because if I multiply those together, it gives me 16. B to the 8th, I broke that down as b to the 2nd to the 4th. That way when I go to rewrite it, The only thing I'm left with is my b to the second, a to the fourth, and 3. All right? Because everything that's not inside the parentheses becomes squared, if you will. So you bring out everything in the parentheses, which in our case, the 3 came out, the a to the fourth came out, and the b squared came out. And that gave us our answer right here. And again, I'm going to post all these so you guys can kind of see what I've done. And again, if you have any questions, you guys have my information, such as text me, call me, FaceTime me, and I don't care to go over this with you guys. All right, so that is example 2. Let's go ahead and now if we could look at example 3. A lot of the same concepts are going to apply here. All right, so here our first problem tells us that we're going to be looking at 25x to the 14th. Well, something that you automatically need to think of, and one thing I want to make sure that you guys are going to see, this time we're bringing out absolute value because it says when n is even because the principal root is desired. So when I'm talking about your principal root is going to be like x can't be by itself if it's not connected. And what I'm talking about is, all right, let's go here and just look where I worked it out. We were given 25x to the 14th, okay? What gives me 25? 5 times 5, correct? Well, how would I write that? Since this is, if this is an understood 2, I'll go ahead and put this right there. It's an understood 2 if it doesn't show any number higher than 2. So I've already got 5 squared, right? So that means I need something that's going to give me a square on the outside. All right? So I'm going to have x, because 7 times 2 is going to give me what? Back to my x to the 14th. So if I bring this out, can you guys tell me what it's going to be? That's going to be 5, because I squared the 5 squared, brought it outside here. This is no longer needed, and it's going to be the absolute value, all right, absolute value of 7. Because what we're doing here is we've dropped an even power. This is not an even power, it's a what? It's odd. So we're going to have, again, so the nth root, and I want you guys to see right here what I'm talking about. Absolute value if n is even, x if n is odd. So, and what that's talking about right here is, when you guys know what I mean when I'm saying nth root. So if this number had stayed, let's just say this would have been 4. This would have been 4, and this would have been 2. Then it would have been just the square root of it. But it's going to have absolute value since we're dealing with negative numbers. If this had been 1, it would have been absolute value. If it had been 2, we would have had a radical. If it had been 3, absolute value. And I guess you know if we had 4, radical. If we had 5, absolute value. Let me turn, oh, sorry about the old hairy legs. Had to turn the old heater off. It's getting a wee bit warm in here, governor. Alright, same concept for, let's go ahead and look at B portion. So we're given negative 49. So what I did here, what I say if it isn't up here, it's an understood square, right? So I already knew that, so I took and got 7 squared. This is already perfect, but I needed to break this down, okay? So, by doing so, what does that give me? I needed to bring the 2 out because I wanted it squared too. So when I go ahead and take my square, that just brings out my, and remember guys, this is negative. I don't know if you saw that over here. But I brought out my negative 7. This is a negative y to the first, okay? Absolute value, it's y to the first. Z to the 6. Z to the 6 isn't where? Z to the 6 is not included in your absolute value. Because it's what? Anybody? I always ask because I know there's no one there. So allow me to answer because it is an even number. Alright, so again, understood square. What's your signs? Let's go ahead and look at the next one on C. Now this looks like a doozy. But guess what? It's not really as bad as it probably presents itself. Here, all we're doing, if you will, we're breaking down. But what's our index this time? It's 4. So that means what we're looking for our exponent is going to be 4. What can give me 4 right here? Well, I already know that a perfect square is going to be what? It's going to be 4. So that's going to give us, because that means if I take a half and a half times a half and a half, that will give me what? The 16th I'm looking for. My R right here, I need a 4 on the outside. So the way I'm going to do that is I'm going to have the R2 and the 4 on the outside. That way it's going to cancel. Now something you're going to see a little different here is you're going to notice this S3 minus 8. Now I broke my 20 down 5 and 4. That way it cancels out the end. Can't really do nothing with the S and the 3 or the 8 at the moment. So I'm going to rewrite down here. I got 1/2 to the 4th from here. R2 4 from breaking the 8. R2 4. Sorry, I think I wrote that down twice. Did I write that down twice? I did, sorry. That's only should be one time. Let me mark that out. So R2 4. 5 3. I don't know why I said 5 because it's definitely S. S3 minus 8. 5 4. Now I want to bring it out like I'm squaring. When I bring this out, it becomes 1/2. The 4 disappears. I bring the R2. 4 is gone. S3 minus 8. 4 is gone. So S3 was what? It was a negative. So I mean odd integer. I'm sorry. So odd. Therefore, it's an absolute value. So we have 1/2 R squared absolute value S3 minus 8 in absolute value to the 5th power. And I want to post all this so you guys can see my workouts. All right, flip on over to page 290 and we'll just keep moseying right along. I worked this one out step by step because the book isn't kind of very, very clear. And I think the way I did it will be a little bit easier. It says that we're going to simplify 192A, A to the 5th, B to the 10th. If you'll notice right here, they said how they did theirs. They did 2 to the 6th. I just went ahead over here. I went ahead and wrote break down the 3, which is your index, when possible. So what you want to do is factor out a number like a perfect square that's going to give you 192. I found out it was 64, all right, of 192. Because 64 is going to be, and they did that right here, because 2 to the 6th power gives you 64. For me, it's easier to do 4 to the 3rd power. Same thing. So I rewrote it as 4 to the 3rd because that gave me 64. Next thing I did is I factored out my A to the 3, which, why did I do that? Because what's our index? Okay, I want my index at somewhere to match. Rewrote it, so I got 4 to the 3rd times 3A to the 3rd, A to the 2nd. All right. If you'll notice, I do have my A3 in here, right? So do not forget when your variables right here are together, you add. If it's on the outside, you multiply. Okay, when they're together right here, like A times A, you add exponents. B the 10th. So the next thing I want to do is factor out B 10th. I want to bring out B 9. Why do I want to do that? Because eventually I need to get back up here where I can get a 3. So I take B 9, and if I factor out B 9 and B to the 1st, you add the 9 and 1, that still gives you your 10. So I rewrite it. Now I can start bringing some stuff out, okay? So sorry if it's, my writing, as always, is not that great. I got 4AB to the 3rd times 3. I did so I can bring this out. All right, now I have 3A to the 2nd, B to the 2nd. So how did I get the A to the 2nd, B to the 2nd? Well, because 3a squared, because if you multiply 3 times a, that gives you what? 9. B to the first is still right here. But I broke that down so I can get rid and make a perfect square. So when I bring it out, I have my 4ab, as you guys can see there, to the third. Now that's not talking about this third, it's talking about what's in parentheses. You're bringing out what's in parentheses, okay? I can't bring this out because there was no way to make it my index. All right, so 3 didn't have anything perfect to go into it, so it had to stay in my radical. The only thing I could bring out was this. So again, I'll let you guys take a little look. If you need to pause it right here and just take a look at step by step to see how we got down here. And again, I'll post all this online also. All right, let's look at example 5. Example 5, we're dealing with negatives and decimals again. Here we got 0.008. It does not matter if it's 0.000000008. We know something that goes into 8 3 times because our index is 3. What is it? It's going to be 2 to the third. So if we go over here and look where we started working out, we're bringing out our index is 3. So I know right here I brought down negative 0.2 to the third because if I multiply that, that gives me 0.008. I bring down my x to the second. Now here I want to bring down my y, but I want to make sure it gives me my index somewhere, if possible. And it does because I can break 9 down to 3 and 3. All right. So 3 times 3 is what? The 9. Now here's where it gets a little tricky. Pay attention. Z to the 7th, I broke it down 3 different ways. All right. I broke it down Z to the 2nd to the 3rd in order to give me 6. Because here you multiply, all right? And since you're multiplying, because if you multiply this together, it gives you Z to the 6th times Z to the 1st. So you add those and it gives you Z to the 7th. But I broke it down this way. That way I can multiply these two if needed and bring this out by himself. So here's my index I needed for right here. And that gives me Z to the 2nd, Z to the 1st. Now I want to go ahead and bring everything out to solve. All right, bring out all my 3's. I was able to bring out negative 2y to the 3rd. Okay. But it's not this third. It's the one in parentheses. Okay, look at the ones in parentheses. That's what comes out. So 2, y to the 3rd, z to the 2nd. All right, now I want you guys to see you're still keeping your radical 3 x to the 2nd because x to the 2nd never stood a chance. It couldn't come out. There was no way. So, because you couldn't take a perfect cube of it. So it had to stay in. X to the 2nd, z to the 1st. Had to stay in because there was no index that would go into that. So our index was 3. That's the reason we keep it wrote like this. So we brought this down. Y and z. X and z had to stay in. All right, let's look at B. B said that we have 320x, y to the 3rd, z to the 4th. Same concept as before. I'm bringing down my 320. 8 went in there. 8 to the 2nd times 5. So that gave me 64 times 5 gives you 320. All right. Since there's nothing here, it's an understood what? It's an understood 2. So it's 5x to the 2nd, what I needed right there. We got y to the 2nd. But how did I get y to the 2nd? Well, I broke it down as y to the 2nd, y to the 1st, because when you add them, it gives you y to the 3rd. Z to the 4th, perfect square. So I broke it down. All right. So now I can start bringing things out. I brought down my 8. I brought down my x and y because x was perfect. And I put it here. Y, perfect square, here. Now I have z to the 2nd. It's here. And remember, you can bring this out because it's inside the parentheses. Because it gives you the z to the fourth right here. Now I need to take the square root of 5y. Why did I take the 5y? Because it was connected here. Okay? There was nothing perfect that could go into that. I mean, realistically, this was the perfect square to give me 64. That's the only reason it could come out. We didn't have like the perfect square of 25 because the exponent was connected here. No exponent, exponent. So do not get confused about that. So quick recap, 320, 64 times 5, 320. X squared, y. So 2 plus 1, z, 2 plus 2, because we're adding exponents. We're looking for something that's going to give us an index of 2. So 2 and 2, we bring those down. X, this is absolute value because it's odd. Z the second stays outside because it's even. Square root of 5y. All right, and our last one here is going to be talking about Heron's formula. Now, it's a little bit different because you're dealing with triangles. We know that interior angle of a triangle always equals 180 degrees. Here we're going to be, I'm just going to zoom out a little bit because you guys are going to have to see this step by step. Now, Heron's formula says that we're starting with a plus b plus c divided by 2. So I drew my triangle right here. It gave me the sides. So I have 81, 45, and, why can't I say 54? 54. All right. Those are our lengths, okay? So that's side A plus B plus C, if you will. So I had those, and our formula says that you take A plus B plus C, divide by 2. I did so, and I got 90, if you can see right here. So 90 is going to start us off when we put everything inside a radical. So in order to find out what we need is we're going to take the subtraction from what we have. So we have 90. We're going to take 90 minus 81, 90 minus 54, and 90 minus 45. Okay, so when I do so, I keep my 90 on the outskirts. 9, 36, 45. Now what I want to do is I want to start breaking these down and see if I can find any perfect squares. Why? Because it's understood 2 here, all the way down. So we have 2, 9, and 5. So that's going to be 2 times 9, which gives me what? 18 times 5 gives you 90. Now if you have 3 times 2, it gives you 9. 4 times 9, 36. 9 times 5, 45. So we've got them broken down in exponential form that we have now some perfect squares. We want to add exponents when we can. Well, what do you mean add exponents? That means any 2's. So you got 2, 2. So that's 2 to the first plus 2 to the second. And that's the only 2, so that gave me 2 to the third. Let's look at 3's. 3 to the second. 3 to the second's 4. 6, 8. 5 and 5. So it's 5 to the first and 5 to the first is what? 25. So when I multiply all those together after finding them, that's 8. It gives us 65, 61 times 25. So I'm multiplying all these together. So when I do, it gives us this huge stinking number of 1,312,200. You're going to divide that by 2 to try to find a perfect square. All right. So what I did is I took that number, divided it by 2, and when I did, I got this number, 656,100. Then I put that in my calculator and squared it. When I did, it became a perfect square. It was a perfect square of 810. Now I took 810 because 810 times 2 gives me what? What gives me back to 65, 61. So when I wrote it here, I squared it, and it gave me 810 times the square root of 2 because I used it twice. They were both inside what? My radical, if you will. Because, again, the number when I do this, it should give me that big number I told you guys right here a second ago. So here's my perfect square. it got brought out. What stayed in the radical? The 2. All right. So again, this is a super large problem, but you can freeze it right here. Take a look at it. And if you got any questions, feel free to ask me and I'll hook you guys up. Hope this wasn't too crazy. I just thought I'd try a different style on this one because I felt like it would be better if I worked them out for you guys. But if you have any questions, you guys know my number.